Let's go to our next speaker, artificial intelligence that is capable of generating realistic sounds and pics and texts. Just recently we thought it's something real, but now it's possible thanks to diffusion models, a new standard of generative AI offering unlimited opportunities in various areas. Our next speaker is Tanika Gupta, head of data science in Sigmoid. She'll speak about how diffusion models work, how can they they can be adapted for specific tasks, and why this is an instrument for the future for various areas, from design down to medicine. Let's welcome Tanika Gupta, please. You're welcome. Dear friends, let's applaud.
Over to you.
Hi everyone, I'm Tanika, and today I'll be talking about the topic mastering diffusion models using prompting and fine-tuning techniques. Before I start, a brief intro about myself. I'm Director Data Science at Sigmoid, where I lead the development of generative AI and machine learning solutions for CPG and financial service industry. I have more than 12 years of experience in data science, having worked in companies like MasterCard, American Express, and JP Morgan Chase. Prior to joining Sigmoid, I was Vice President Machine Learning at JP Morgan Chase, where I was leading the development of fraud models for their consumer card portfolio. And I have 3 ideas which have been filed for patent protection and have won numerous hackathons in the past. And on a personal front, I'm a long-distance runner, having completed more than 10 half marathons. So before I start the session, there's a question I have for you. Looking at all these images, anyone can guess what is special about all of them? Anyone wants to take a guess? OK, maybe after the session, you would be able to answer this question. So all of these images have been created using diffusion models. And I would be covering about how exactly that happens today. So these pictures were generated by Stable Diffusion. You might have heard about DALL-E 3, which is similar to Stable Diffusion. And in this session today, you will understand the concept of how diffusion models work and how they have revolutionized the generative AI industry. So one of the things you can do using diffusion models is you can give a text prompt. So for example, over here, you can see a cat, which is in a form of a Van Gogh painting. So you give a prompt that I want to have an image of a cat in a Van Gogh painting, and you can get an image. And there's a whole concept, right? There's a whole science behind how this actually gets generated, which we will learn in today's session. So today's session, there are 4 key points which I'm going to cover. The first is about understanding about how diffusion models work, what is basically the concept and mechanics behind this, how these models are actually able to generate high-quality images by series of iterations and refinements which they do. We'll also cover about how you can actually use text prompting to refine your image outputs, which is your visual prompting. And finally, the last topic which I'm going to cover is on image inpainting, which basically focuses on how you can replace a certain part of an image with a new image. And again, this is a revolutionary concept because what it does is that you have a certain image and you do not want to modify the whole image, and there's a certain area which you want to modify or enhance. You can do that using Stable Diffusion. So what exactly are Stable Diffusion? I think I've spoken it about 10, 15 times since I started. So what exactly these models do are, they are advanced machine learning algorithms which progressively add noise to your data and then remove that noise to create new synthetic data. So this is, again, a concept, right? Like what it is basically doing is from noise able to generate new content, new synthetic data. So you can imagine, right, like, right now, we are talking about generative AI, about new ideas, new synthetic data being created. The basic concept over here is that we have noise as an input, which basically gets refined and improved over a series of iteration, and we are able to get a new synthetic or a new image data which you had never seen before. And the various applications of Stable Diffusion, there are various applications across various domains. The first one is inpainting, which I again spoke about, where you replace a certain part of an image or modify or enhance with a new image. The second is text to image, which again I've discussed in the starting of the presentation, where you can give a text prompt and actually get a new image. So like you can say that an astronaut is riding a horse. You saw that image in the starting. Using Stable Diffusion, you can create a new image, which basically is able to follow the prompt. The third is drug discovery. Again, you can use Stable Diffusion to actually create new molecular structures. And the concept remains the same. You start with noise, gradually refine and enhance, remove that noise, and create a new data. Autonomous vehicles. Again, you can use Stable Diffusion to create new complex traffic scenarios, which can then be used by these autonomous vehicles to test. So you can test those autonomous vehicles on these complex traffic scenarios, which, which has never been generated before. Medical imaging. This is again another area where Stable Diffusion is being used, where what you do is that you can actually enhance the quality of your medical images by gradually denoising. So a lot of the medical images or the data which gets created, you don't have a lot of, the quality is not good. But with Stable Diffusion, you can actually enhance those quality by gradually refining and reducing the noise. So now you understood, right, what exactly the basic concept and mechanics behind Stable Diffusion. Now, in the next session, we will actually cover those in detail, how exactly this happens, how exactly the models, gradually refines those noise to create a new synthetic image data. So in this session, I'm mostly covering about image, but it can also be used for images, audio, video, any kind of data. The concept remains the same, that you start with noise and gradually refine and iterate to create new data. So for this, to explain you about this concept in detail, I'm going to take an example of a sprite. So sprites are your 2D graphics data, which are used in computer graphics like computer vision, video games. So now, in a scenario like you have a lot of sprites data, and you want to create a new sprites, how you can do that using Stable Diffusion. So what you want is that you want the model to actually learn about the fine details, right? So when you're training a model using an existing sprite data, you would want that it learns about these fine details like the hair of the sprite, the buckle on the belt, right? Or some general outlines, how the whole shape of a sprite looks like. So the way it does is, we'll go to the training part. So this is how the training happens for a diffusion in a diffusion model. So you provide sprite as an input, right? And you also provide noise. So you add noise to the sprite image, and this is fed as an input to your neural network. So the neural network learns to predict the noise. So it's not predicting the image or the sprite over here, it's predicting the noise. And once you have outputted noise, what happens is that you try to see what is the loss, which is basically the difference between the predicted and the actual noise which was given as an input. Now, this loss is back-propagated, and the model keeps on refining. So you provide different images, you provide those noise, and you train the model to gradually enhance and improve. And this is how the model gets trained. So this is how you train a Stable Diffusion model, by giving it an image as well as noise as an input. Now, once the model has been trained, the next part which comes is the sampling. So in sampling, what you do is that now you want to create a new image. Now you have a trained model which is able to, which has learned those features, right? Those finer details and the gradual outlines of your sprite. Now you want to generate a new data, which is your new sprite. How will it happen? So this is the sampling process. And what happens over here is that you feed a noisy sample. So it's a Gaussian distribution. It's a simple, noisy sample which is fed as an input to your trained neural network. And again, the predicted sample, like I said in the previous slide, it predicts the noise. So you predict the noise from that noisy sample, and then you remove that noise from the input to get an output. Now, since you're predicting, right, you won't be able to reduce that noise in the first iteration. So you do multiple iterations till you finally are able to get a proper image of a new sprite, which is a new sprite altogether. It's a new data which has never, the model never, it was not used in the training set. Another important thing to take care over here, like when I spoke about the process, right, you have an input data, you add those noise, and you predict and you remove. But what happens is that while you're training, while you're doing the sampling, you have to add the noise back in the first process. So you gave an input of a noisy sample, the model predicted and predicted the noise, you removed it. But you again add back certain noise, because if you don't do that, what will happen is that your final output of a new sprite would look like something like this, which is basically an average of all data sets. So to avoid that and to actually get new sprites of very high quality, this is one, again, an important step in your model training where you add those noise back to the data. Now, I'll cover this concept of embedding, and this is very important. So if you remember, one of the applications which I spoke about was text to image. So right now we spoke about how you can create new images using noisy sample, right? You give a noisy sample as an input, and the model is iteratively refining it to create a new image altogether. But you also saw an application where you can give a prompt. So I can give a prompt, right, that I am sitting on a moon. Now, how will the model actually be able to use this prompt to create an image of me sitting on a moon? So this is, for this, an important concept to understand is embedding. So embedding is a concept where you basically have a text data, and you actually use it to create into a vector format. And an important thing to take care over here is to understand over here is that embeddings, or basically text which are similar in context or meaning, would have their vector formats also very similar in values. So for example, you can see one calculation over here, right? Paris minus France. Since Paris is the capital of France, if you do that vector calculation of Paris minus France of England, you would get a London vector format for London. So this is all basically because the embedding is able to capture the semantic meaning of the text as well. Now, how do you use the concept of embedding and diffusion, which we learned, to actually create text to image? So we already understood that part, right, about how we actually start with a noisy sample, right? We actually train a neural network. Now, the training, basically from the, when we are training with context means that we are training it with a prompt as well. So you can see, in the last process, we only had an image. We had a noisy sample, which was given as an input to the neural network. Now, over here, we have a text prompt as well. So the text prompt in the first is a ripe avocado. Now, this is a prompt which I'm giving to the model to understand that this is a ripe avocado. And along with, so what happens over here, this ripe avocado is converted using embedding, the concept we learned in the last slide, into a vector format. So now you have a vector format of the ripe avocado. You also have the image and the noise, right? All of this goes into your training model. Again, the concept remains the same. The model learns about all these finer details about the avocado and about all the generic details, and also it learns the context, which is a ripe avocado. Now, similarly, like, you have a lot of data, a comfy chair. All of these are used in training. Now, what it helps is, now once this training is done, during sampling process, you can give a prompt, which the model has never, ever seen. So over here, it is an avocado armchair. So the model was not trained on it. Now you give during sampling, which is basically, after training, you are actually generating new output. You give an avocado armchair, you give a noise distribution, a sample noise, as an input to your trained neural network. Now with this, you can see that finally the model is actually able to, you predict noise, you remove that noise, and through an iteration. Again, in this slide, we don't see those 500 iterations, but after those 500 iterations, you would be finally able to generate a new image. And the new image over here is, as you can see, of an avocado in the form of an armchair. So this is, again, you would probably have used an application in the past, or you might use in future. I will definitely recommend, if you're not done, there are a lot of applications available on the internet to generate new images. I think it's, so if you do that, this is how it's working in the background, right? This is the whole concept behind it. Now we understood, like we have covered 2 sections. We understood about how diffusion models, what exactly diffusion models do, how the working looks like. Now let's go to the next part, which is the visual prompting. So this is about how we can actually use prompts to modify our images. So over here, you can see that if you give a prompt something like highlight the dog on the left, you can actually do operations on your images using visual prompting. And before I go into more details about it, one concept I want to explain it to everyone, like about object detection versus image segmentation. And I often see that people get confused between both of them. So object detection is basically, it specifies the object in your image. So it's basically a concept to understand that where exactly, if you want to detect an object in your image, you use an object detection. But the drawback is that you have a boundary box in form of a rectangle or a square, but you're not able to actually get to understand the shape of the image. And that is what image segmentation comes into play, where it actually creates a pixel-level mask, pixel-wide mask on an object, so you can actually get the shape of the image as well. We have OWL VIT, which is a zero-shot object detection model. This, again, is one of the most common models used for object detection. And we'll understand this whole image pipeline in the next few slides, image editing pipeline. So OWL model is basically used to detect objects into an image. And since it is zero shot, you need very few samples to actually train your model. And what it also means is that if you have not trained your model on any of those objects, still it would be able to detect those objects in your image. The next concept is about segment anything model. So segment anything is basically about, again, the image segmentation. You give an image as an input, it takes boundary box or pixel coordinates as an input, and it's able to generate all the images, basically a mask of the images. So over here, it generates the top 3 valid masks. So this is how your whole image editing pipeline looks like. So you started with, you gave an instruction to the model that highlight the dog on the left. You gave an image as an input. What happened in the background is that you have an object detection model which actually detects this particular object. And then you have a segment anything model which is able to create those masks. And I think, in the next slide, you will understand how this actually helps in image in painting as well. So now if you understood how the whole image editing pipeline looks like, now we'll go to the image in painting and try to understand how we can actually leverage to actually replace a certain image, certain part of the image with a new part. So image in painting, like we already discussed, is replacing a certain part. So over here, you can see that this is a very simple image where you have a tree, and you can replace it with a dog. Now, how does it function? You can actually do that. There are a lot of applications available on the internet where you can replace maybe your ex with your new boyfriend or girlfriend. So if you want to do that, right, you would be able to do it on using that application. But what exactly is happening in the background? So this is how you gave an input image. You say that over here you can see an image of a shoes, and you are giving an input prompt that replace this running shoes with my formal shoes. So you saw the image editing pipeline we had in the background. We started with an input image. The object detection model actually detects that there is shoes over there. Then the segment anything model actually creates a mask. So you can see the masked image over here. This is being created using both the concept of object detection as well as the segment anything model. Post that, you are able to create a pixel-wise mask on the image, and then you are able to replace it and create replace it with a formal shoes. So this is how the whole functioning or the concept behind image in painting is. Now there are some parameters which are very, very important when we talk about diffusion models. So the 4 parameters which are very important are your guidance scales. So guidance scale is basically a value which determines how closely the model should follow the prompt. So the prompt is the instruction. So like over here, I'm saying an oil painting of a tabby cat dressed like a character in the Matrix. So if this is the instruction you gave that you want to generate an image like this, in a scenario where you have a guidance scale value, right, the higher the guidance scale value, the higher the model will try to follow that prompt. But what it does is that it reduces the quality of the image. So over here, you can see that our guidance scale 7.5, it's not exactly matching the prompt in terms of the instruction we have given, but the quality is better than probably the quality we have at guidance scale value 15. Another important hyperparameter we have is the inference steps. Now, the inference steps, so you remember the concept of how we spoke about different iterations we have to do while creating the diffusion model. We start with the first iteration, predict the noise, remove that noise from the input, and gradually we do those 500 iterations to finally come up with the final new image of a sprite. Now, those are the inference steps, those 500 iterations. Now, the more steps you have, like you could see that it was improving with each and every step. But again, the compute would be more. The more the steps you have, the more the compute it takes, right, to run the model. So that is a basically thing you have to take in care. You want a better quality image, or you want to reduce the compute power, and depending on that, you can decide the value of inference steps you want to take. Another important parameter in diffusion model is your strength parameter. Now, strength parameter plays a very crucial role because it determines the level of noise that is added. Now, you have all understood about noise, right? How noise can also be very powerful. Over here, we have noise, which is we are using it to create new synthetic data. Now, the amount of noise you add actually increases the randomness of your final generated output. So, so if you look over here, we have this prompt of a cute baby bear eating burger at home. Now, the more strength parameter, which basically means the more noise, you can see that the quality is more random. It doesn't follow the prompt. So you have to decide between how much creative we want to be. And the ideal ideal value for a strength parameter would be somewhere between 0.4 to 0.6. And the last is the hyperparameters, your negative prompt, which basically tells the model what it should not do. So a negative prompt is basically, a lot of time if you try to generate images, right, using the applications which are available on the internet, you would say that you will see that they will generate images in form of cartoons or, which don't look realistic. So you can actually specify that in your prompt that you don't want an image which basically is, looks like a cartoon. So in that scenario, you will ensure that you have an image which looks real. That's all I have for today. I hope you really enjoyed the session, and I'm looking forward to, actually, like you said, that diffusion model is a revolutionary concept. It can be used to generate a lot of new synthetic data, and I do hope that after this, you do go try and using these models and creating some innovative applications, or using them for your day-to-day or in your professional environment. So, do reach out to me. This is my LinkedIn QR code. In case you have any questions, I know we are short of time, but do reach out to me in case you have any questions or you want to discuss. I'm always looking to have those discussions and discussions with everyone so that I can also learn from each other. We can learn from each other. So thank you.
We did enjoy your presentation. Thank you so much for sharing your knowledge and experience with us. We really appreciate it. Thank you so much.
Thank you.
Give a big round of applause for our Tanika Gupta. Thank you.